Okay, ready for last hour? Okay, before I start, was this too slow, too fast? Too slow? Too fast? Okay, I have an idea. Everybody close your eyes. Okay, now you have to say too slow, too fast, or good. Okay, no, you need to close your eyes. Everybody close your eyes. Okay, too slow? Too fast? Good?
Good.
Okay. Okay, thank you.
Hand up. Two hands up. Oh, what is it for?
All good. They're all good, passed. Okay. Okay, great. Okay, so I want to say first, one thing I forgot to mention about the sum check protocol that we'll actually use later. It has a nice property, which is, look at what, so the prover sends polynomials, low-degree polynomials. What does the verifier send? The verifier just sends random field elements. So really, randomness. He chooses random, like log f bits and send them over. Okay, this is called a public coin protocol. Public coin meaning the coins of, so each round you should think the verifier chooses coins and just sends them publicly to the prover. Like, here are my log f coins, here you go, this defines a field element, and that's my field element. Okay? This kind of public coin protocols are very useful because we can later, as we'll see in this class, we can use cryptography to eliminate this interaction from this protocol. So the fact that it's public coin, we'll come back to it. Okay? But just notice the verifier's message is truly random. Okay. One more. Okay. Yeah, sorry.
Just wondering, are there also protocols where the prover has randomness?
Good. So okay. So as I said, we mentioned the verifier has to be randomized. If it's not randomized, the interactive protocol has no power. The question here was, does the prover need to be randomized? Is it helpful if he's randomized? And the answer is, it doesn't help him to be randomized because you can always fix his coins. The verifier doesn't. It's the okay. When is it helpful for the prover to have randomness? When you want to hide. When we do zero knowledge, where the goal is kind of to hide things, then the verifier has random coins that the verifier doesn't know, but in this case, the verifier is not. We're not trying to protect the verifier. So why is randomness is helpful? Why is it important that the verifier uses randomness? Because the prover needs to send the polynomial. He should not know which element t the verifier will send. If he knew on which point t he will be asked, then he can cheat. He'll give you a false polynomial that happened to coincide with a true polynomial at that point t. There are d such points, so he can choose it. He can choose the fake polynomial to kind of coincide. The power comes from the fact that the prover doesn't know this t. So we don't trust the prover, and we use randomness kind of against it. The verifier is trusted. We're not trying, so it doesn't help the prover to use randomness in a sense. Or in other words, you can just fix, you can fix this randomness once and for all time. Think of him as kind of a non-uniform prover, and that's it. The verifier is not going to change his behavior depending on, because he's honest. The verifier is always honest. It's the prover, malicious prover, that we're worried about. And therefore, the prover doesn't help him he doesn't need randomness, because you can always hardwire the best randomness possible to him, and now he's just a non-uniform kind of machine, a circuit, as opposed to kind of a randomized machine. So in this context, randomness to the prover is not needed, but randomness to the verifier is paramount.
So when you say public coin, does that mean the prover can't see those bits?
No, public coin means that the verifier doesn't hide anything. Of course, the prover, good question, thank you. The prover, he never sees the coins in advance. So if he saw the coins before he said anything, he can cheat. But the verifier never hides coins to himself. So public coin means when the verifier just sends random coins. So I'm the verifier. You guys gave me a univariate polynomial, a degree d polynomial. I choose coins, a field element, that's kind of random coins, I send it over. I don't keep any state, all my messages are just random. You say, give me another polynomial, I'll just send randomness. That's the definition of a public coin protocol. Okay, so public coin protocol just means, so node sum check is a public coin protocol, which means that verifiers' messages are truly random, just random bits. Or I should say uniform. I just said random bits, truly uniform bits. That's what public coin means. Yes?
I guess, like, is it known what happens if the prover does know all the randomness in advance?
Yeah, yeah. If the prover knows all the randomness in advance, he can cheat. Why? Let me tell you how I'm going to cheat. So I'm a cheating prover. Let's say before we started, you gave me all your T1 up to Tn. Actually, even if you just gave me T1, I'm golden. Why? I faked. I said the sum is B. It's not beta. It's not beta. It's something else. Now, all I want is to find a univariate polynomial that sums to beta. So it's not the true polynomial. It sums to beta, but it agrees with a true polynomial only on T1. Because once it agrees with T1, from now on, I need to prove a true statement. Because I need to prove this, which is actually a true statement. So I'm good. So if I knew T1, I can always kind of come up with such a polynomial. The thing is, I don't know what T1 is. So actually, I want to give, Chinmay actually asked me a very good question in the break. And I want to give kind of Chinmay's geometric interpretation of the soundness proof. Okay, so let me give you kind of a geometric interpretation of why this protocol is sound. What's happening in this protocol? So here's the geometric interpretation. We have a little box, h to the m. You can think of it, this is kind of the little box h to the m. I want to prove to you that this low degree polynomial, if you sum over the value in this point, all these h to the m points, it's beta. Now let's look at the big F. I have like this big F. I don't know, right? Okay, now what happens? If you were incorrect, if you cheated me, then this sum, you sum over all the points. Let's fix this point here, like the one possible h1. Maybe what you gave me is false. What you gave me is this sum is either false on h1 or on h2. Somewhere it must be false, because if it was true on everything, it would be true. So you gave me something that's false on one of them. I don't know which one. Now, so what I know, but now I'm going to use error correction to say, well, if it was false on one of them, it's false on a random point, T1. So now I forget about this sum. I just look at T1, and I know that the sum only over the rest of the dimension 2 is false on T1. And now again, false on T1, that means H2, one of them must be false. I go to kind of a random point in the extension, and there, with high probability, it's false. And kind of this is how I bop around from kind of dimensions, so T1, T2, third dimension T3, T4, and so on, up to the point that I get a random point in kind of F to there. Okay, so that's kind of a geometric interpretation of what's going on. Okay? Okay. Any questions? Okay, so we saw the sum check. So let's see where we are. We introduced this interactive proof model. We saw sum check protocol. Seems kind of very specific. Let's try to see why it's very interesting, the sum check protocol. So first, before as first thing, let me give you an example where the sum check is useful. And here's the example. Let me show you that sharp set has an interactive proof. IT is the set of all languages that have interactive proofs. So let me prove to you that sharp set has an interactive proof. That's an example. This will use the sum check protocol. By the way, let me just mention, all the examples that I'm giving you are not just examples, okay? I'm teaching something through it. So don't just add the example, I'll kind of forget about it. Okay, they're specially crafted. Okay, so what is sharp set? Sharp set, we're giving a formula. phi, and we're asking what is the number of satisfying assignments to this formula. That's the question. That's the aim. So phi is, you should think of it as a Boolean formula. We're given a Boolean formula. Let's say phi is over, like it takes, over, let's say, n variables. And Boolean formula, just think of like it's and or. And we have NOT gates. Okay? And the question is, what one is how many assignments over 0, 1 to the n make this formula accept? That's the question. Okay? So, by the way, when we say formula, we mean it's a binary. Think of it as a binary tree. So a formula is just a binary tree. Each gate, you can think of it as an and or an or. And then the final leaves are kind of all kind of xi or not xi. Okay, so phi is of the following form. It's, let's say, and then you can have or and, so on and so forth. And at the end, it has like x3, not x7, and so on and so forth. Okay, so you can think of the size of this formula is the number of leaves. Because up to a factor of 2, it's like the number of gates, the number of leaves, it's kind of the same. Okay, so, and just note, x3 may appear many times, because I really opened it up to a tree. Okay? So each variable here can appear many times. So this is what a formula is. And sharp set, so now I want to say that, let's say, phi and k is in sharp set. It's in the language, if and only if phi has, so the number, if you look at all the x's in 0, 1 to the n, such that phi of x is 1, this set equals k. Okay, if there's exactly k satisfying assignments. Okay. Questions about this language, 3 set? We're good? Okay, I just want to point out a formula is different than a circuit in the sense that the formula is a tree, it's a binary tree. A circuit is kind of an arbitrary directed acyclic graph. Okay, and in particular, in a circuit, in a formula, you need to kind of recompute everything. So if this gate uses a value and this gate also uses the same value, you need to recompute it. You need to compute it kind of twice. In a circuit, it can do things much more efficiently. Okay, so there's also circuit set. That's a sharp circuit set. That's a different problem. Here we're talking about sharp set for formulas, okay, for trees. Okay, so I'm going to give you actually, so this is known to be a very hard problem. You know, I'm giving you, like, think of 3 set. You know, it's NP complete. Now look at the number, like, it's NP, but number, like, how do you know how many satisfying assignments it has? It's considered a very hard problem. But you know, if you think about it, it's really surprising that you can give an interactive proof for it, which is really nice. And moreover, the interactive proof is really just the sum check. That's all. That's all it is. So I'm going to show you how I embed this kind of question into a sum check. Okay, and note that this is just a Boolean formula. Where's the polynomial? Where's, you know, I'm going to make a sum check, but to have sum check, I need a polynomial. And this is just a Boolean formula. So the way, the idea is to use, so I'm going to use sum check for this IP. And the way I'm going to use sum check is by a technique called arithmetization, which we'll use. Okay, so I'm going to, so the idea of using sum check, or the idea behind this IP, is to arithmetize the formula phi. Okay, so I want to prove to you that phi comma k is in sharp set. I want to use a sum check protocol. That's the only protocol I know. And I want to use it. But I need a polynomial. So how I need to sum polynomial and to sum over this polynomial. What is this polynomial? It's going to be an arithmetization of the set formula. So how do I arithmetize? The idea is very simple. I'm going to convert any, so this is a Boolean, this is Boolean, it's all over 0, 1. Yeah, I have and or, everything is over 0, 1. I'm going to convert an AND gate into mult gate. Okay, so actually fix any finite field. You can make it very, very big, so you'll have good soundness. So, okay, with respect to field, finite field F. So fix any finite field. Okay, it can be very large. I'm going to convert any AND gate into a multiplication gate. So mult is just take x and y and just output x times y in the field. Okay, but in particular, what it means, if there's anything times 0 is 0, and 1 times 1 is 1. It's exactly an AND gate. Okay, if I have an OR gate into, so this is a bit more problem. So this is going to be, so actually let me say, maybe I'll write it. So I'm going to write AND of x, y. I'm just going to write as x times y. And I'm going to write OR of x and y. Any idea? Yeah?
X, Y plus X plus Y.
Exactly. Exactly. X plus y, that's the idea. But of course, then it's 2. I mean, so I subtract x times y. Exactly. Okay, so of course, 0 goes to 0. If only one of them is 1, you get 1 and 0, nothing. And if both of them are 1, then this one is 1, so it takes care of it. Good. And then the NOT, I go into NOT of x is simply what? Exactly, 1 minus x. So now I have actually an arithmetic circuit. Okay, so this arithmetization allowed me to go from a circuit into an arithmetic circuit, or from a formula, sorry, into an arithmetic circuit. And now note, let's look at first note that each gate is now an arithmetic circuit of size at most 3, right? It's a tiny circuit, like this is, so each gate really is only blew up at only a constant. And now really what I want to do the subject over, my protocol, what I want is to look at, so let's denote the arithmetization by, so if we denote arithmetized formula by phi tilde. Okay, so phi tilde goes from f to the n to f. It's just addition multiplication. You can define over the big F. Yes?
I'm worried that since OR now has x twice and y twice, since you said it has to be a tree, you have to copy and paste y in order to plug it into that.
Okay, actually I don't care. We'll see.
Sure.
You're saying what you're saying is wait, y is in middle, y is in all I care is that I started with a formula. I don't care in the middle what I do with it.
So right now it's not a formula anymore.
Yeah, oh, sorry. Good, thank you. Good, thank you very much. Thank you. Great. Well, you guys are good. Thank you. Okay, so let's denote the arithmetized version by phi tilde. Now, of course, it's natural. What would be the subject protocol that makes sense to do at this point? Any ideas? Exactly, exactly. Let's prove that sum of phi tilde over b1 up to bn in 0, 1 is equal to k. Why that makes sense? The only thing we need to be careful with is what is the degree of this thing. So now let's just argue that the degree is not too big. Okay, but if I convince you that the degree is small, then we're done. We just do a sum check. And this is exactly what you want to prove. Okay, so let's just make sure that the degree, so n here, like the number of rounds, is going to be n. There's going to be a degree d. We just need to ensure that d times n is much, much, much smaller than f. which governs, I put here which governs the soundness. Okay, so let's just see the degree. So here's a claim. The degree of phi tilde is at most, or let me write it differently, the sum, let's look at the degree for each variable, okay? The sum of the degree I, for variable I of phi, so we have n variables, x1 up to xn, each one has some degree. The sum of these degrees, I'm going to argue, is at most s. S being the number of S size of phi, which is defined to be, this is by definition, the number of leaves. In phi. Okay, so let me argue that the size is at most phi. The degree is at most the sum of the degrees at most s, or the size. Okay. By the way, before actually I do that, just to make sure, because I actually noticed that I glossed over it too quickly, I said that, this is all we need to prove, but I just want to make sure, is it clear that phi tilde and 0, 1 to the n is actually equals to phi? Yeah, that's very important, because we want to make sure that we're actually summing over the actual phi, like in 0, 1, because we want to prove sharp set of the phi formula, right? And the reason is, as we said, is that on 0, 1, we really behave like the and and or. So, of course, outside of 0, 1, who knows? We're over a big field, who knows what's going on? But on 0, 1, we behave exactly like the and and or, like the original tree, and therefore, this arithmetic formula is actually equal to the original formula on 0, 1 to the n. Yeah? Okay. So, good. So this is what we want to prove. Now let's just look at the degree. Yeah?
Degree sub 5.
Good, good, good. This just means this is the degree of xi in phi. So I'm just going to, yeah, or in other words, I can argue that each variable has degree at most s. But I can argue something stronger, the sum of the degrees of all the variables is at most s. Okay, note that s is polynomial here. Okay, we have this, that's the input. The input is a stat formula, it's polynomial. So as long as this is the degree, we're happy. The communication complexity, the verifier complexity is going to be n, the number of variables, d, which is like s, polynomial, and polylog in the field. So so the verifier is going to be polynomial. Okay, now we care about, now there's a notion of polynomial time verifier. Okay, but if the degree is at most s is polynomial, we're good. Okay. So why is this the degree? So to prove that this is the degree, the proof of this claim is by induction. It's actually a pretty straightforward proof, and it really uses the fact that phi is a formula, that the original phi is a formula. So let's see. So the proof is just by induction. And here's how, okay. So we're going to prove by induction on the depth of this formula. And so, okay, if we have just one gate, then, okay, it's clear the degree is just 1. So that's fine. So if number of gates, or the depth, if you want, is 1, then, of course, the degree is going to be less than the size. The degree is just 1. That's if you just have a single gate. And now, if you have a more general, so now suppose you have a circuit of the form, let's say add or mult, it doesn't matter, or and, you can have like phi1, suppose phi is phi1 and or I don't care, phi2. Okay, this can, we tell us generally and, but of course it can be also an or. Then, how do we arithmetize this? So now, what is phi tilde? Phi tilde is going to be either a phi1 tilde times phi2 tilde, or in the case of, this is for and, if it was or, then it would be phi1 tilde plus phi2 tilde minus phi1 tilde times phi2 tilde. Right? All of them, of course, over x1 of the xn over x1 of the xn. Yeah? Okay. So let's look at the, I want to argue that the arithmetic version is of the sum of the degrees of all the variables at most s. So let's see. Let's look at phi tilde. If phi tilde was, if the original phi was and of phi1 and phi2, then phi tilde is just the multiplication, by definition, we replaced and with multiplication, of the phi1 tilde polynomial times phi2 tilde polynomial. But what do we know here? Here, the degree of each, so now let's suppose, okay, suppose phi1, let's say it's of size S1. And suppose phi2 is of size S2. Okay, I'm just, now what we know that the size of phi S is equal to S1 plus S2 because it's a tree. So there's no kind of, everything is open. So the left side of the tree is S1, size of S1. The right side of the tree is size S2. The entire tree is the size S, which is S1 plus S2. So now, what is the, so what can we say in this case? So let's focus on the and. The or is exactly the same. So what can we say about the sum of the degrees? So sum of degree, the degree of the ith element of xi in phi is equal sum n I. What is the degree of the ith variable in phi? It's the degree here plus the degree here. When you multiply things, I need to sum the degrees. So it's the degree of xi in phi1 tilde plus the degree of variable I in phi2 tilde. Right? When I have two polynomials, multiply, the degree adds. But this is just S1 plus S2 by induction, by the induction hypothesis. Okay, so the degree here, the sum of the degrees is like the size of the formulas. We actually don't really care about the sum, we care about the degree itself, but this kind of shows you, at least the degree of each one is also almost the size of the formula, and therefore the soundness, so now when we run, so let me put this back up. So we run the sum check on this polynomial, and we get the communication complexity and the verify runtime will be n, or the number of variables here, n, times the degree, which is s, essentially the size of the input, right? That's s, and polylog the field. Okay, so you just need to take, and similarly, and the verify, yeah, the degree, which is s, the completeness is always 1, and the soundness, importantly, the soundness of this protocol is n, the number of variables, the degree, which is s, divided by the size of f. So all we need to make sure is to arithmetize with a field that's significantly larger than n times s. And this will be the soundness error. Okay, and of course, then you can repeat all this to get errors those you want. Okay? Any, yeah, questions?
So
You can go first.
Okay. So when you do the sum check, like when the sum is happening, is that like necessarily a sum over the field, or can it be like any sum over like a different field? Or like if your like original field is just like I don't know some prime field or something.
So okay, just note in this specific problem, I don't have an original field actually. For this specific sharp set, I'm over 0, 1. There's no field. It's not an algebraic. It's a Boolean thing. I don't have any polynomial, any algebra, any field, nothing. I just have 0, 1, and I have AND and OR gates. To prove that the number of satisfying assignment in the Boolean cube is k, I choose a field of my liking, and I arithmetize. I think of this circuit as polynomials, as having addition and multiplication gates. And I think, in my head, I think of this circuit as this formula as a polynomial. So I choose the field. It's not actually the problem. I on purpose kind of chose a field so that I can do the sum check protocol.
Right. Yeah. But I guess like what I'm asking is like when you like for the sum in the sum check, like let's say you like not for this problem.
Oh, I see. You're saying in general, you're saying, look, let's say you have a sum check problem. Someone gave you a sum check problem, and you're not happy with the field. The field is not good enough for you, or it doesn't give you enough soundness. Can you amplify? Can you work over a different field? Is that what you're asking?
Or I guess what I'm asking is like if you have sum check and like there is some field, like let's say you're working mod like some large prime or something.
Good.
But then like the sum, like will the sum that you're doing be like also over that field necessarily? Like can you?
Okay, so
just change
when
the field up?
good. So when I do a sum check over the field, everything will be over that field. Yes, everything will be over the field. However, that said, if I'm not happy with the P, if you're saying, so I got a sum check protocol with certain P, over GF2, GFP, so everything is mod P with certain P. Now, yes, everything should be over this field. Now you can say, well, this P is not that great because it's not that much bigger than M times D, and I'm not really happy with this field. Or maybe even it's smaller than N times D for all I know. It's not a good field, not big enough. Then what do I do? So I'm saying, it's okay, don't worry. Just take an extension field. Instead of working over P, you work over kind of GFP to the N. So you can take a field of size P to the N for any N that you want. And you're only going to pay kind of polynomially or linearly with this N. So, and then you can amplify your soundness.
Okay. I was just wondering because I was wondering what happens if K is like larger than the size of the field or something.
Oh, I'm going to choose the field to be much bigger.
Okay, I see.
Yeah, I'm going to choose the field. Otherwise, you can't. Yeah, I'll need to choose the field to be much bigger than K. Yeah.
So like.
Oh,
we
sorry,
okay.
I forgot you. Yeah. Okay, yeah.
This is kind of related to the point, but we need to choose a field that has like really big characteristics, so we need to like choose a really big prime number. We can't just do we can't just raise it to the n.
Oh.
Because K can be like 2 to the n.
You can choose a prime field that's bigger than K.
Yeah, no, but the question is, can you? No, but the question. Well. Okay, if you. Okay, in our case, you can just choose the field to be as big as you want. In the case where you're given a sum check, of course the sum is in the field. It's something about the field. You're given something about the field, so K will always be in the field.
But for the sharp.
For this specific one, I'm thinking of, you choose a K that's bigger. However, I'm not 100% sure that, let me think. Can you use small characteristic? Yeah, that's what I'm thinking. I'm not sure if you can't use some Chinese remainder trick and use over a small characteristic. I need to think about it. But anyway, in this case, just choose after the GFP for a large P, and that's bigger than K. Yeah. Sorry, Rahul, did you have a question?
Oh, I was just going to ask, is this the only way we know how to do foot sharp set RP?
This is easy. What do you mean the only? Do you want it easier?
Yeah, I mean, it's easy, it's nice. I was just wondering.
So no, I think this is the simplest way. So let me just say, so we put sharp sat into IP in this way. You can ask, what about, let's say, sharp circuit sat, which is the same thing, but we're giving a circuit. So we're given a circuit, and you want to know how many satisfying assignment does it have over 0, 1 to then. It's the same thing, except for phi is now, it's not a tree anymore. It's a directed acyclic graph. So, and it turns out that it also has an IP because it's in P space. You can go over all possible x's x1 up to xn and check if it's satisfying or not in its small space. So it's in p space. And so you can ask, okay, so what about this? Now you can't do some check because the degree won't be small. So actually you can do it, but that's much, much more complicated and requires this kind of degree reduction thing. That's kind of how Shamir proves IP equals P space. There's some degree reduction there that really complicates matters. So you'll need that for a circuit set. But for SAT, because it's so low degree immediately, it's kind of nice, and that's all you do. Yeah, you should be, you should. Where's the gratitude?
So I guess reinterpretation of Rahul's question, I suppose, is suppose you're given another problem, let's say permanent or something, right? So I want to, I guess it's not formally defined, but I want to direct kind of without reducing to kind of like sharp SAT and so forth. I mean, I want to direct protocol. It's not very well defined.
Yeah. So I have to say, almost all the protocols I know for IP go through some check.
Actually, there's this weird one by like, I might be wrong. I thought that the Rita Harnum was one of the authors and not the other one, but there's this weird one that goes through like a quantum problem. Like if they were trying to prove, verification, information theoretic verification for BQB and they failed, and they got like sharp peers in IP in some other way. So,
Okay, so I'm not familiar with that, but I think the main ones go through some check.
What I remember is they're like doing this. It's sort of like some check, but they're also like looking at like reduced densities over the subgates and stuff, which is.
Any other questions about sharp set? Yeah.
Yeah, because the sum check protocol is like, I believe it's operating over a field, like all the summation goes to the field.
Right. Yeah.
So does that mean that we, to be safe, to ensure correctness, we must ensure the field has characteristic greater than the number of satisfying solutions?
Yeah, exactly.
In this case, 2 to the n.
Yes, but the verifier runs in time log in this circuit. So in the log in the size of the field. Yeah, log in the size of the field. So the field can be 2 to the n.
Yeah, that's a requirement. You can't pick small characteristic field.
Yeah. So okay. I would. So what we should do is take GFP, large field, large characteristic. I'm not sure you can take small characteristic actually. I need to think about it because maybe some Chinese remainder theorem can help you.
Oh, but that would require extension, not using the field.
No. What Surya said, right? We run this protocol over many small primes, right?
Yeah.
And make sure that the answers are all sort of the number of sets.
Oh,
yeah.
CRT, and that's what
Yeah.
CRT is about.
Yeah,
Or
exactly.
running multiple times.
Yeah, exactly.
You would need the fact that those primes should be larger than k anyway. So
Yeah,
it doesn't really
so-
help.
It does. Yeah.
So the field
Why
size
doesn't it
has to be
help?
larger than
Because
Yeah.
part of these primes has to be larger than
Right,
so
but-
communication
I think
complexity
maybe
is
it's
part.
Yeah. But it's
No,
but if you don't want to, sometimes.
Actually, I'm not so sure, right? Because the computational complexity is going to be is probably going to be smaller. Instead of log a big field size to the power 3 or something, right? You have sum of log small size fields to the power 3. Which is
I see, yeah.
Anyway,
And you can parallelize.
you can parallelize.
Yeah.
It's a long.
Okay, so by the way, just note about the prover runtime here. Of course, is large because he needs to find the set. I mean, what can you do? He needs to at least count the number of satisfying assignments. It takes 2 to the n at least, right, to find them, and then, okay. So far we gave some examples. So where are we, right? We talked about IP. We showed the magical, amazing sum check protocol. We showed how to use the sum check protocol to give an IP for an inductive proof for sharp SAT. In some sense, maybe you're not so blown away at this point because actually sharp SAT, like a formula is really, arithmetization is not like, wow, we all know that and is like multiplication and or can be written as like small arithmetic thing. So it's actually an arithmetic circuit. So it actually gives you yourself a low degree polynomial. So some sense it calls for a sum check. It is a sum check. Like without much change, it's like already it presents itself almost as a sum check. So maybe you're not convinced of the generality of the sum check. And the next thing I want to do is kind of show you actually a completely different thing that doesn't seem to be at all low degree or anything, and try to show you how you can use the sum check. And actually, this takes us a kind of a nice way into the idea of doubly efficient proofs. So far, when we talked about interactive proofs, our focus was the verifier is efficient, he's polynomial time. The prover can be whatever. And indeed, in the protocols, both sum check and sharp set, of course the prover runs in exponential time. He has no choice, he needs to do the computation. Okay. The idea that, so now let's kind of shift gears and talk about the notion of a doubly efficient interactive proof. So the notion of a doubly efficient interactive proof, the idea is actually, you know what, so the main idea is we care about the runtime of the prover. So the prover is not all powerful. It kind of brings us kind of to real life, okay? It's very nice that the verifier is polynomial and the prover is all powerful. But guess what? All powerful doesn't exist. Everything is limited to some extent. There's more powerful and less powerful, but there's not all powerful. So what we want is, yes, the prover is more powerful than the verifier, otherwise we don't need it. The verifier doesn't need him. But even the prover is not all powerful. So in a doubly efficient interactive proof, we want to say the prover has a problem at hand, and he should not spend too much overhead in convincing the verifier that the solution is that his solution, that, you know, let's say that X is in the language. Okay? And this is kind of interesting even if the problem, so when we talk about doubly efficient interactive proofs, we even care of problems in P. So often when we talk about interactive proof, we think even, let's say the problem is polynomial time. So I have I want to argue proofs of polynomial time, you know, a language, but I want the verifier, let's say the time to determine this language as, I don't know, n to the fourth. I want the verifier to be linear time. Okay, so the idea is there should always be a gap between how powerful the prover is and the verifier is weaker. But I really care about both. I care the verifier should be very, very efficient, and the prover should also be somewhat efficient. Okay, that's the idea. So, okay, so what is a doubly efficient interactive proof? So a doubly efficient, let's say for example, L in some d time t, so can be computed in deterministic time t. Again, you can think of t even to be n to the fourth. Okay, can be polynomial. Is an IP where the prover runtime, the honest prover's runtime is only polynomial overhead in the time of determining the language. Okay, so if it takes time t to determine, he runs the time at most poly t. And the verifier runtime should be much, much less. Okay, ideally, we want the verifier to run in time like almost linear or quasi-linear. So n polylog n, let's say, which is denoted by O tilde of n. Okay, so ideally, we want the verifier to run in linear time or quasi-linear time. And the prover should not have too much overhead. Actually, ideally, the prover should also have just linear overhead. Okay, but definitely, by definition, it should not have more than polynomial overhead. And sorry, yes, thank you. And this is T of n. N is the size, yes. So of course the verifier needs to read the instance, but not do much more than that. Okay, so it's just interactive proof where we care about both the prover and the verifier. Okay, and yeah, and so let me mention that these things that people actually care about because they use it in these blockchain protocols and so on. And so they really actually, a lot of work that's done on this, and I think in the lecture notes of Justin Taylor, I'm now going to refer to these sections so we won't cover them, but they exist sections where he really talks about the exact kind of parameters, the exact numbers, the exact implementations, and so on and so forth. Because these are things that actually people care about because they want to run it. So actually we really care about, you know, the overheads here in practice at least. Okay. So now, so far we said the sum check is really, it's this, of course it's like, it seems like outside the realm even of double efficiency, but actually now let me show you a specific example, which again is beyond just an example, because we'll use it to teach something, where it's actually in P, and I'll show you an interactive proof for this problem, okay? Using the sum check protocol. A doubly efficient interactive proof for this problem. Yeah?
Can you clarify what is like T and like the D time?
Good. Yeah. So take any problem, any language, for which membership in this language can be decided in time T. Okay, so D time T means there's a deterministic algorithm that runs in time T. What T is, it can be anything. You can think of T as n to the 4th, n to the 10th, n to the log n, quasi-poly, whatever. All I care, so of course, the prover needs to compute. If he's proving something, he needs to know that it's true. So he needs to do this deterministic computation. So of course he needs to run in time T, but should not run in much more than T. And by not more, theorists say poly T, applied people say linear in T, the real applied, say not more than 128, whatever. But yeah, depending how far you are in that spectrum. Okay, so good. So now let me show you how a doubly efficient interactive proof for counting the number of triangles in a graph. Okay, that's the example. Next week, I'm going to show you actually interactive proof for doubly efficient interactive proof for all low-depth circuits. So I'm going to generalize it by a lot. But let's start with like an example. Okay. So let's say we're given a graph, G, and we want to count the number of triangles in the graph. Okay, so given G, so we want an interactive proof for counting number of triangles in a graph G, with vertices V and edges E. Okay, so I want to cast it as a doubly efficient sum check protocol, kind of sum check protocol, but so notice this is a problem in P. I can go over all possible 3 vertices, triplets of vertices, and check if there's a triangle. So I can check this problem time n to the 3rd. I want my verifier to be linear. So I want a prover that runs in time not much more than n to the 3rd, or let's say polynomial time, to convince a linear verifier that this graph has let's say exactly k triangles. And I want to cast it somehow in a sum check protocol. So how do I do that? So first I need to come up with a polynomial, right? I need to embed a polynomial here. Note there's nothing polynomial-like here. Talk about graphs. Okay. So remember how originally I told you everything is a polynomial. Everything can become a polynomial. This is an example that kind of shows you why you take anything and make it a polynomial. So what is the idea? Let's look at the adjacency matrix corresponding to this graph. Okay, that checks if there's an edge between a pair of vertices. Now we can write this matrix as a function f that goes from, let's say, v, like number of vertices times number of vertices, to 0, 1. It takes a pair of vertices, output 0 if there's no edge, 1 if there's an edge. Let's denote the number of vertices here by n. So sorry, I denoted there the input length by n, close enough. It's not really the input length, the number of vertices, but it's denoted by n. Okay, so now we can think of the adjacency matrix as a function. So think of the adjacency matrix. Let me write it as a function, f, that goes from 0, 1 to the log n. I'm going to assume that n is a power of 2. It goes from, so it takes, I'm going to think of a vertex. So v, as I said, is of size n. Write it here so it won't be in my way. I'm going to think of the function as taking a pair of vertices where I represent a vertex as a vector in 0, 1 to the log n, okay, and any number of n, like binary representation of the, I think of the vertices as numbers between 1 and n. I'm thinking of the binary representation. And I output 0, 1, whether there's an edge or whether there's no edge between these vertices, these two vertices. Okay, so this says 1, if and only if there exists an edge between the two vertices. Okay, now suppose you want to argue that the number of triangles is, let's say, k. So what do you need to prove? You need to prove that the sum over all I, j, and k in n, or let me even make myself in 0, 1 to the log n to make it easy for myself, because I'm representing in binary. So for any 3 vertices, let's count the number of triangles. So when there's a triangle, if I and j are connected, this is 1, and f, j, k is connected, this is 1, and f, I, k is connected, this is 1. They all need to be connected in order for it to be a triangle. Okay, so now note if they're all, so if it's a triangle, I get 1. If it's not a triangle, I get 0, because one of them is going to be a 0. So I want to count the number of triangles. And I want to check that this is k. Almost, I lied a little bit. I kind of overcounted because there's permutation, ijk, jki, so I need to divide by 1 over 6, which is the number of ways to permute any ijk, because any ijk is counted like all permutations. So this is what I want to prove. Okay, I want to prove that the sum of all possible triangles ijk, I counted each ijk here essentially 6 times, so I need to divide by 1 over 6. The number of triangles is k. Okay, almost. At least I have sum. It's getting to look like a sum check, but there's no algebra. And there's no algebra. I just wrote in numbers. I mean, I took binary representation. But at least, you know, I have some sum. So if I had some nice algebra here, if this was all over a finite field, and let's say this f was also low degree, then I can use sum check. Okay, so again, suppose this was over a finite field, and suppose this f was very low degree, and the field was large, so we have good soundness. I want to prove sum of this big F is k, sum check. So I just need to kind of tell you how do I add algebra? Where to make this degree, low degree, and where does the finite field come from, and so on. I'll do that, but before I'll do that, also note the sum here is only over 0, 1 to the 3 log n, right? So it's actually, remember the problem was the prover runtime is very large. It's h to the m times the time it takes to compute one function, and times this m. This m is going to be small, but the h to the m is the problem. But here, h to the m is just 2 to the 3 log n, 2 to the log n, so it's boundary. So if I'm able to put like a sum check, like a algebra here, I will get double, the prover will still be polynomial time, which is what I want. Okay, the question is, how do I put algebra here? Okay, so this is where so I'll say a little bit about this, and then we'll break for today and continue next week. But there's a generic way to convert any function into a polynomial, okay? And the way to do it is via a technique called low degree extension. So if you actually remember the way I started class with an example of the matrix multiplication. And if you remember in the matrix multiplication, there's no polynomial, it's a matrix, nothing. But what we did, the randomized algorithm that we showed, we thought of a row in the matrix as a polynomial. So we took a row which consists of n elements, and we thought about it as a univariate polynomial of degree n. Remember, we thought of like rho is like coefficients of the polynomial. So we thought of it as a polynomial of degree n minus 1, I guess. So n elements, one is the free coefficient, so degree n minus 1. So we started already the class with an example that I have a row, nothing, no algebra, nothing, an arbitrary row of a matrix. And we converted it to a univariate polynomial of degree n, like the length of the row. What we do here is a very similar idea, but in the multivariate setting. Okay, so what we can do, we could have taken any n elements, that row, for example, or in this case, like the elements are all the kind of, for any f you can think of it, it's like a matrix, right? It's like n squared elements if you want. For any two elements, whether there's a edge or not an edge. So you can think of it as n squared elements. It doesn't matter. We can take any set of elements and convert it either to a univariate polynomial, as we did before, of that degree, or that's not good for us, because here the degree is going to be n squared. It's already, like the verifier runs in the degree and more, it's not going to be efficient enough. But the idea is we can convert it to a multivariate polynomial with much, much smaller degree. Okay, and that's what's called the low degree extension. So whereas before we just did a univariate polynomial, so we had to kind of put the n elements kind of as coefficients, each one kind of added a degree, if you will. If we put it in a multivariate polynomial, so if we think of it like as a polynomial over, let's say, h to the m, then we can stack inside h to the m, we can stack n points. We can make h and n much smaller, both h and n to be much, much smaller than m. And that's kind of what we're going to do. So let me explain this more precisely. Okay. Okay, so here's the theorem we're going to use for this. So take for any function, not polynomial, can be arbitrary, like the adjacency matrix function. For any function f, there it's like from 0, 1 to the 2 log n. But let me take it more generally, from h to the m to 0, 1. Again, in this example, h is just 0, 1, and m is like 2 log n, because we have there 2 log n. But let me give you something more generally. So take any function. Okay, this is essentially any set. You can think of this. This is any set of, this is kind of equivalent to any element in 0, 1 to the h to the m. Right, so it's just a string of binary string of length h to the m. So take any binary string of length h to the m. Okay, it just tells you for each element h to the m what the value is, 0 or 1. So for any function and any finite field, f, that contains h, of course, in that example, 0, 1, f contains any f contains 0 and 1, so that's not a problem. There exists a unique, what's called low degree extension. I'll explain what this means in a second. It's a function f tilde from f to the n to f, such that, so in what sense is it low degree extension? First, it's an extension, namely f tilde. If you look at an h to the n, for the element on the little cube, it's exactly f. So it extends f. F was an h to the n, f tilde is on a bigger cube, it extends. So on the small cube, they agree. The second thing is that it's low degree. So it's a low degree extension and a low degree. How low? So f tilde is of degree h minus 1 in each variable. Okay, so again, what is the theorem? The theorem is you can take any set. If you want, you can take any set. So let's say of n numbers, take any set, let's say, fix any vector. Let's say W, in let's say 0, 1 to the n. You can always embed it. You can think of W, an equivalent way is to think of W, oh, sorry, I meant to say, sorry, as a field, let's say W1 up to Wn, in 0, 1 to the n. You can embed it. You can think of it as a function from h to the n to 0, 1, as long as h to the n is n. So you have a long sequence of 0, 1s. Fold it into a nice kind of, a cube of size h to the n. So essentially, you should think of the h-ary representation of n, okay, the h-ary representation. So you just kind of, h to the m is equivalent to the set. You can think of a bijection between that and all the numbers between 0, 1 to, between 1 up to n. And now the claim is, actually you can take this stuff, so this is the, let's say, h by m. You can kind of extend it to a bigger function, tilde, over f. This is over f to the m, such that it has degree h minus 1 in each variable. So just note, if we think of m as being 1, the univariate case is exactly what we had before. If you had just a string of like size, if n is 1, h essentially is like n. Okay, I take n, I just expand it in this way to a degree n. But then the degree is very large. That's not good. Like the verifier runs in times the degree. That's awful. So I make the degree much smaller. How do I make the degree much smaller? I add more variables. So the idea is add many more variables. Now in each dimension, the degree is only h. Because now I don't need the size of h is n, but h to the m is n. And now in each dimension, the number of elements is like h. So on each dimension, the degree will be h minus 1 instead of n minus 1, like it was in the univariate case. I'll prove all this, but this is just kind of a high-level idea. Okay, so again, the high-level idea, we'll go into the proof next time of this theorem, but the high-level idea is, we all know by the kind of the univariate case that you can take any string of length n and code it as a univariate function of degree n minus 1 there's two ways of doing it. Either by thinking of the string as the coefficients, that's one way to do it. Another way to do it, which is how the low degree extension works, is by thinking of the string as the value of the polynomial in, let's say, polynomial value on 1, 2, 3 up to n. Let's say 1 up to n is in the field. So think of GFP, let's say. Here, what we do, we take your points, we take a polynomial f for which your points are sitting in this small cube. So let's say you have a vector of size 1 up to n. We'll put here W1, W2, W3, WH, all the W's we'll put here. And then the theorem says there's a way to extend this entire thing into a bigger polynomial of degree h minus 1 in each variable, such that if you look at the polynomial on this cube, it's exactly what we had before. So you have your kind of vector, or your function from h to the n, to 0, 1. Here, and the rest is just extended. And it's extended in a way that the degree of each variable is h minus 1. Okay, so for example, if you want h to the n to be n, what you can take, for example, is h to be log n. The degree is only log n, which is great. And you can take n to be even smaller than log n. If you do the math, it's going to be log n over log n. And note that the verifier runs in time that depends on n, m, h, and d is going to be also h. So all of it is going to be polylog, which is great. Okay, so next time what we're going to do is prove this low degree extension theorem, and then show how to use it first for the triangle. That would be pretty immediate, and then we'll show how to use it for kind of a general low depth circuit. Okay, thanks.